Hey everyone, and welcome, focused learners, to another edition of The Explainer. I am absolutely thrilled you're here today because we're taking something that probably sits on your kitchen counter right now, and we're going to completely change the way you look at it. We're going to demystify bread making. For so many people, baking bread feels like this intimidating, mystical art form where you just kind of cross your fingers and pray the dough actually rises. But today, we're flipping the script. We're going to turn that art into an incredibly approachable, fascinating, and truly living science project. Because once you understand the mechanics happening at a microscopic level, you have the ultimate power to create literally whatever you want.
So, here is our roadmap for today. 1. The soul of bread. 2. The science of dough. 3. The Texas bread ratios. And 4. Masterclass on the artisan baguette.
Let's dive into Section 1, the soul of bread, a historical context.
Before we get into the nitty-gritty chemistry, I think it's vital to just pause and reflect on the sheer scale of bread's existence in human history. This isn't just another recipe, right? It's literally the dietary bedrock of humanity. Over 10,000 years ago, our ancestors were taking simple crushed grains, mixing them with water, and baking them on hot stones. It was about pure primal survival. But as we moved into ancient times, bread became the literal foundation of civilization. Being able to harvest wheat, store it, and bake it, well, that meant people could actually settle in one place. It built cities, it built entire economies. And yet, for thousands of years, bakers didn't really know why their bread rose. They just knew it worked. Today, though, we have the immense privilege of seeing it for what it truly is, a living science project. Every single time you mix flour and water, you are setting up a complex biological environment. And honestly, that is incredibly exciting. Moving right along to Section 2, the science of dough, foundational chemistry.
So here's the most encouraging thing I can tell you if you're a beginner. The ingredients actually do all the heavy lifting. Your only job is just to manage their environment. Think of flour as the skeleton. When you take dry flour and hydrate it with water, you trigger a chemical reaction that creates gluten. Now, gluten is basically a stretchy, elastic web. Without it, your dough would just be a sad puddle of mush. This gluten network provides the physical structure. It's the architectural framework that holds the dough shape and gives it that wonderful, chewy bite we all love.
And now, for our second main character, yeast. If gluten is the skeleton, yeast is absolutely the engine of your bread. Yeast isn't just some inert powder you buy in a little packet. It is a tiny, single-celled, living organism. And just like us, it needs food to survive. When it wakes up in your dough, it immediately starts hunting for the natural sugars present in the flour to consume. It is the biological motor that is driving this entire operation. So really, it's the ultimate partnership. Flour gives us the architectural skeleton. Yeast gives us the engine power. One provides the structure, the other provides the action. They are entirely codependent. I mean, you can't build a house without a frame, and an engine is pretty useless without a chassis to actually move. So, we have our stretchy web, and we have our very hungry living organisms. Which leads us to a pretty fundamental question. Why exactly does dough rise? Like, what is physically happening inside that bowl sitting on your counter during the proofing stage?
Well, here is the biochemistry made super simple. As the yeast eats the sugars in your dough, it digests them and actually breathes out carbon dioxide gas. Remember that stretchy gluten skeleton we just talked about? Well, it acts like a trap. As the yeast exhales, that carbon dioxide gas gets caught in the stretchy gluten web, inflating it like thousands of tiny little balloons. Those little balloons of yeast breath are what physically push the dough up and outward. They are literally the exact same air pockets you see when you slice into a beautifully baked loaf.
So the crucial takeaway here is this. Without those tiny bubbles of CO2 pushing the dough up, you wouldn't have bread at all. You would just have a flat, dense, heavy cracker. The entire magic of baking lies in trapping that gas effectively before you lock the structure into place inside a really hot oven.
Which brings us to Section 3, the Texas bread ratios, scaling the math.
Now that we understand the core science of flour, yeast, and hydration, let's look at how we scale these principles to make different things. But before we look at the numbers, I want to share a really fascinating regional variable, the Texas theory of dough. In environments with super high humidity, like Texas, your dry flour actually absorbs and holds extra ambient moisture straight from the air. It's a fantastic reminder that baking is a living science. Your local environment genuinely affects your baseline dough. You always, always have to pay attention to what the dough is telling you, not just what the recipe on a piece of paper says.
Okay, let's look at some ratios.
For lean, crusty standard breads, think of a classic French baguette or a traditional Mexican bolillo. You're typically looking at a 3-to-1 ratio. That's about 3 cups of flour to 1 cup of water. It makes a sturdy, really easy to handle dough. But let's say you want to make ciabatta, which is famous for those massive airy holes inside. To get that, you actually have to increase the hydration. The ratio drops to roughly 2.5 cups of flour to 1 cup of water. It's a much wetter, stickier dough to work with, but that extra water creates more steam in the oven, giving you that incredibly open, airy texture. But what happens when we want something a bit richer? That's when we introduce enriched doughs. And oh man, this opens up an entirely different world of treats. We're talking yeast donuts, chewy bagels, famous sweet and savory Texas kolaches, soft dinner rolls, and even some really cool sourdough variations.
The secret code to making these enriched treats is actually surprisingly simple. Lean doughs rely purely on water, right? They give us those crispy crusts and chewy interiors. Enriched doughs take that baseline 3-to-1 ratio, but we completely swap the water out for milk, and we add fats like butter or egg yolks. The fat actually coats the gluten strands, which physically prevents them from getting too stretchy. This creates what bakers call a short crumb, which is just a technical way to describe that ridiculously soft, tender, melt-in-your-mouth texture you experience when you bite into a fresh kolache or a warm glazed donut.
All right, Section 4, Masterclass, the artisan baguette, the overnight process. Let's bring all this foundational science and ratio math together into one incredibly practical application, the revered artisan baguette. Step 1, we start with the bloom. You take your yeast, warm water, and a little pinch of sugar and just mix it together. You are literally waking the yeast up from hibernation, giving it a nice warm bath in a sugary snack. Once it gets frothy on top, you know it's alive and ready to go. Step 2. We mix in our flour, using that trusty 3-to-1 ratio, and we are physically developing that gluten skeleton. And you'll know you're done when the dough passes the window pane test, meaning you can stretch a little piece of it so incredibly thin that light passes right through it without the dough tearing. Step 3, we cover it, and we just let it rest overnight at room temperature. Now, you might be wondering, why on earth do we let it rest overnight instead of just baking it immediately? Because time is an ingredient, folks. That overnight room temperature proofing is where the absolute magic happens. It's called long, slow fermentation. While you're sleeping, the yeast is slowly eating, producing CO2, and releasing organic acids and alcohol straight into the dough. This slow chemical party is exactly what develops the incredible depth, that slight tang, and the complex flavors that elevate just a basic loaf of bread into a true artisan masterpiece. And that brings us to the end of our explainer. We've traced bread all the way from ancient stones to the modern science of yeast and gluten. We've seen how tweaking simple ratios can conjure up everything from a crusty bolillo to a soft, buttery donut. You now understand the code. You know the engine, and you know the skeleton. So I'm going to leave you with this question. How will you manipulate your own living science project now that you know the code? The next time you step into your kitchen, don't just blindly follow a recipe. Experiment, observe, and bake with absolute confidence. Thank you so much for joining me today, and as always, keep learning.